Are there any questions about isotopes or atomic weights? What is an atomic weight? You read off the periodic table.
It is the average of the...
Yeah, the weighted average. We need to look at it again. So we're going to look at chlorine for an example. So chlorine has two naturally occurring isotopes. We might call them stable, meaning we find those on the surface of the earth. When you put some sodium chloride on your French fries, you're going to be ingesting two flavors of chlorine, chlorine 35 and chlorine 37. So how many protons in this isotope? Was that? Yeah, 17. And how many here? Yeah, because if it had something different, it wouldn't be chlorine. Very good. So this weighs something like this. It has an abundance of about 75.8%. So we want to do something with this data. And you nicely told me that what you read on the periodic table is the weighted average of the percents. So one way you might want to think about percent, 75.8% means 75.8 out of 100. Out of 100 grams of chlorine samples, 75.8 is going to be chlorine 35. Of course, this will give us a decimal fraction. And then I need to sum that with 24% or 24.2 grams of chlorine 37 out of every 100 grams of chlorine sample. And chlorine 37 weighs 36.95903 atomic mass units. And this is going to be the atomic weight, what we're going to see on the periodic table. Now, of course, on my calculator, unless it's like 0.5% or 1%, then I might divide by 100 to make sure I get the decimal in the right spot. But if you've done enough of these, you're just going to go 0.758 multiply 3496 and sum that with, and I wouldn't have to do this, but I went ahead and found 75.8% of 34.968852, and I went ahead and found 24% of 36.965903. I'm going to get busy and cut to the chase here. And so when we look up at the periodic table, what we see is a little square up there, and it's got chlorine in it. It says 17 up there, and what do we see right here? 35.45. And that one goes a little further, slightly different than mine. Any questions about this process? So the atomic weight we see off the periodic table represents the weighted average of all the naturally occurring isotopes. Naturally occurring means we find them on the surface of the earth. Unnatural isotopes are ones that get made in nuclear reactions, particle accelerators, and a few other ways, like maybe in the upper atmosphere, and they decay real quick and we don't see them. So that's what naturally occurring means. Any questions on this? How many of you want to see the same problem but in a more exciting way? Tough crowd. So the other day when I talked about this, we mentioned carbon. What are some common isotopes of carbon? 12 and 13. How much does an atom of C12 weigh? And we could put a lot of zeros. It's an exact number by the definition of science. So that's what my ellipsis means. It goes on forever. Atomic mass units. Now, carbon 13, we're going to look in a mass spectrometer, and that might be the limit of the mass spectrometer. So how many digits do we know the atomic mass of a carbon 13 atom? How many significant digits in that number? 5. Good. Just trying to wake you all up with some feedback. Knowing that when we look up on the periodic table, we see something like this. We're going to let X equal the fraction of carbon 12. And so then we can write something like we just saw earlier, where I'm going to have the fraction times 12 AMUs exactly, summed with the fraction of carbon 13 and the mass of carbon 13. And this equals the atomic weight, or the weighted average. So some percentage here, some percentage there. What do I know about X and Y? They're both fractions. What do those two fractions add up to? Now this whole thing sums up to that, but if I add X and Y, what do I get? 100 if it was percentages, and we're gonna just keep it in decimal fractions. So then this equals what? 1, yeah, exactly. So now I can solve for y in terms of x. So I'm going to say y equals, I got a minus x from each side. So I get something that looks like that. So then I'm going to take this equation, I'm going to plug that into equation number 1. So then I'm going to have something that looks like this. X times 12. I'm going to just get rid of those zeros. Summed with 1 minus x times 13.003. That should equal our 12.011. Now it's just what we might call plug and chug. I got 12x plus this 13.003 times 1 minus 13.003x. All that equals 12.011. All right, now I'm going to combine terms. I'm going to subtract 13.003 from that side. Whatever we do to one side of the equal sign, we do to the other. This gives me something like negative 0.992. And that is equal to something like some positive 12 with negative 13.003. We're going to get something that looks like negative 1.003. Subtracting 12 from that. X equals that there. So x is going to equal something like negative 0.992 divided by a negative 1.003. Good thing I moved my camera back. So x equals 0.989. And I said, well, let's not turn our percents into percents by multiplying by 100 up above. I said, let's just keep these decimal fractions so it sums up to 1 instead of 100. Of course, we can, since we use percent quite a bit, there's our natural abundance of carbon-12, 98.9. Now we know what x is, 0.989. What is y? We can come back up here to y and go y equals 1 minus x, something like that. Keep this going on over here, 0.011. or 1.1% of the carbon we find is carbon-13. Any questions? So little harder problem, given the masses of, say, 2 isotopes and the weighted average, figure out the natural abundances. With the chlorine, we had the natural abundances and the weight of each isotope, and we were able to calculate an atomic weight, which is the weighted average of all the naturally occurring isotopes. Fascinating, huh? And just a tiny bit of algebra. How do you feel about the mole? You call an exterminator and you dial 6.022 times 10 to the 23rd, right? 1 mole of copper atoms equals 6.022 times 10 to the 23rd Cu atoms. Well, let's just keep going with this. For fun and no prizes, who can tell me what mass I need to write down here? How many grams of copper equal 1 mole? Yeah, you look up at the periodic table and see 63 point, let me go find it, 546. So when I see something like this, I get way excited because I see a unit equation, and what do we get from unit equations? Unit factors. How many unit factors can I come up with? There's one. There's its reciprocal. How about this one? Then there, of course, is its reciprocal. Are there more unit factors to come up with? Is there an infinite amount or a finite amount? I think I can come up with another one that's going to have 1 mole of copper in Avogadro's number, Cu atoms. I think this is going to about do it. So a unit equation is a statement of 2 things being equal. Presently, I got 3 things being equal. I got this number of carbon atoms. We know that Avogadro's number of whatever that is equals 1 mole of what we're talking about, Cu atoms. And now we use the periodic table and take that atomic weight and put the unit of grams, and that becomes 1 mole. Because we learned the other day that the mole was saying how, if we have exactly 12 grams of carbon-12, the number of carbon-12 atoms in that 12 grams of carbon-12 is a mole and represents a number that's experimentally found, and that is Avogadro's number, 6.022, and then some remainder that I don't have memorized. So all that business of converting milligrams per second to kilograms per year, or milligrams to micrograms. Helps you to know, when do I divide by Avogadro's number? When do I multiply by Avogadro's number? When do I divide by the mass of copper? Here's 2 times I'm going to divide by the mass of copper. Depends on whether I want moles or atoms. So units are our friends here. So I'm going to make up a word problem. How many copper atoms are there in 10.5 grams of copper? Only one place to start with this word problem. So I can look up here at my unit equation and see that this is the mass of a mole, and this is the number of items in a mole. So I'm going to go 63,546 grams of copper, and then you can see my copper unit disappearing. And since I want to use more Expo marker ink, I'm going to just pull out that definition. That's just like putting these two together. Now I'm going to put these two together. And then once you get this far, you can say, am I multiplying when I need to multiply? Am I dividing by what I need to divide by? And the way you answer that question is you say, do my units tell me? When we divide by that weight on the periodic table, we're taking whatever mass of copper here and converting it into moles copper. And then when we multiply by Avogadro's number, we get rid of a mole, and the unit we end up with is copper atoms. And of course, where I was going to go right at the beginning, then I decided to make a joke about using more marker ink. Same thing here, maybe one less step. So 10.5 divided by 63.546 multiplied by 6.022 times 10 to the 23rd equals, there's our answer. And we might say, does it make sense? 10 grams is definitely less than a mole, about 6 times less. And 10 to the 22, that's smaller than 10 to the 23. So that should make sense. All right, do you want to see the Avogadro's number problem that messes up half the students? Yeah, all right. And then I'll explain why it messes them up. What is the mass of 7.8 times 10 to the 24 copper atoms? All right, only one number in unit in my word problem, in grams. So the only thing I can think to do is write down this unit, look up at my handy dandy unit equations above, and say, well, here's where I see this unit, Avogadro's number. That's the same thing as 1 mole, but since you're all sophisticated and you took math 1400, right? Raise your hand if you passed 1400. Close enough to everybody. So I'm going to just link this thing being equal to this mass here. 63. College algebra should be good. We made an exception for you. We know you're studious and driven. Persistence is more important than IQ. All right, so as Orion asked, grams, right? Grams of copper. We see that unit right there. That's why we pulled that out. So everybody needs to do this on their calculator. I'd say in your pod, pull out your calculators. All right, I'm going to write down the correct number on this piece of paper. And then I'm going to do it the way students sometimes do it. Oh, calculator, what's this? I'm gonna use my caret. Does anybody know what the caret is? I can't even do the caret correct, messed up. All right, did anybody get 8.23 times 10 to the 48th? Good, but everybody should have got something like this. You didn't do it. And that makes sense. It's, all right, so sometimes students get this. Whoops, why don't I fix this up? Yeah. All right, which one of these numbers do you think is more reasonable anyway? Yeah, this might weigh more than the Earth, right? Yeah, that's a big number. So I got 2 minutes to explain this. How many of you have spent some time and are intimate with your calculator? One person's acting like they are. The way I type this in is I go 7.8, then I hit the shift and there's this little key that looks like this, and then I go 24, and then I do whatever I want here, times, when I say whatever I want, whatever order, and then I go divide, and I hit this little E key, and I get the correct answer. The one way students like to mess this up is they go times 10 caret 24, then they hit divide, 6.022, then they go multiply, 10 caret 23, and what this does it puts the 10 to the 23 up top. So it's going 10 to the 23rd multiplied 10 to the 24, and that's why you get this like 48 out there.